Quantum physics is the strangest, most mind-bending field of science ever discovered. Unlike the predictable laws of classical physics that govern our everyday world, the quantum realm operates on an entirely different set of rules. Ones that defy logic, break reality, and challenge our fundamental understanding of existence. In this bizarre world, particles can be in two places at once, teleport information instantly across vast distances, and even change their state just because they're being observed. Time might not flow the way we think, and reality itself could be nothing more than a shadow of deeper, hidden processes we have yet to understand. Even space, which seems empty, is constantly fluctuating with energy and virtual particles that pop in and out of existence. The implications of quantum mechanics are not just theoretical. They power modern technology, from computers to lasers, and may hold the key to unlocking quantum computing, teleportation, and even parallel universes. But the deeper we explore, the more reality itself starts to look like something out of a science fiction story. So what are the spookiest, most reality-defying laws of quantum physics? Let's take a dive into the strangest corners of the universe. Wave-particle duality, the ghostly nature of matter and light. One of the most unsettling discoveries in quantum physics is that everything, light, electrons, even atoms, behaves as both a particle and a wave at the same time. This is known as wave-particle duality, and it completely defies our common-sense understanding of reality. In classical physics, objects are either solid particles or spreading waves, but not both. However, in the quantum world, particles like electrons don't follow this rule. If you fire a single electron toward a screen with two slits in it, you might expect it to behave like a tiny bullet, passing through one slit or the other. Instead, it interferes with itself, creating a wave-like pattern on the screen as if it had traveled through both slits at once. But when we place a detector to observe which slit the electron goes through, the interference pattern disappears, and it suddenly behaves like a particle again. This eerie experiment, known as the double-slit experiment, proves that quantum objects exist in a strange, ghostly state of uncertainty until they are measured. Before observation, they are waves of possibilities, but the moment we look at them, they choose to be particles. Does this mean that reality only exists when we observe it? Or is there a deeper layer of the universe where all possibilities exist at once? Wave-particle duality remains one of the most haunting mysteries of quantum physics, hinting that reality itself might not be as solid as we believe. Quantum superposition, being in two places at once. If wave-particle duality wasn't strange enough, quantum mechanics also tells us that particles can exist in multiple states or locations at the same time, a phenomenon known as quantum superposition. Imagine flipping a coin. In our everyday world, the coin must land on either heads or tails. But in the quantum world, a particle can exist in a state where it is both heads and tails simultaneously until someone observes it. The moment it is measured, it collapses into a single outcome. One of the most famous thought experiments illustrating this is Schrödinger's cat paradox. Suppose you place a cat inside a sealed box with a quantum mechanism that has a 50% chance of releasing poison. Until you open the box to check, the cat is neither dead nor alive. It exists in a superposition of both states at once. Only when observed does the cat's fate become definite. Superposition is not just a weird theoretical idea. It is the key to revolutionary technologies like quantum computing. Unlike classical computers, which store information as bits, either 0 or 1, quantum computers use qubits, which can be 0, 1, or both at the same time. This allows them to perform calculations at mind-boggling speeds, solving problems that would take normal computers millions of years. But superposition also raises deep questions. Does reality only choose an outcome when we observe it? If so, what determines which outcome becomes real? And could there be multiple realities where every possible outcome happens simultaneously? As unsettling as it sounds, quantum superposition suggests that the universe is far less definite than we assume, and that reality itself may be shaped by the very act of looking at it. Quantum entanglement, the spooky action at a distance. If superposition wasn't bizarre enough, quantum mechanics introduces something even stranger, quantum entanglement. a phenomenon so eerie that even Albert Einstein called it spooky action at a distance. Entanglement occurs when two or more particles become mysteriously linked, no matter how far apart they are. If you measure one particle's properties, the other instantly reflects that change, even if it's on the other side of the universe. This happens faster than the speed of light, seemingly breaking the laws of physics. Imagine you and a friend each take a pair of quantum-entangled dice. You travel to Mars, while your friend stays on Earth. The moment you roll your die and see a number, your friend's die, no matter how far away, would instantly show a corresponding result. How does the second die know what the first one showed? No signal, no delay, just instant connection. Scientists have tested this again and again, proving that entanglement is real. In fact, in 2017, researchers beamed entangled particles between ground stations and a satellite over 1,200 kilometers apart, confirming that the effect still held over vast distances. But how does it work? Some believe entangled particles communicate through hidden, unknown forces. Others suggest that space itself may be fundamentally interconnected in ways we don't yet understand. A more radical idea is that entanglement hints at the existence of parallel universes where measuring one particle in one reality determines its twin state in another. Regardless of the explanation, entanglement is more than just a spooky curiosity. It's the foundation of quantum teleportation and quantum cryptography, paving the way for ultra-secure communication and future quantum technologies. But if measuring a quantum system changes it, that brings us to another unsettling mystery. What if reality itself depends on observation? The observer effect. Does reality exist without observation? One of the most unsettling principles of quantum physics is the observer effect, the idea that simply looking at something changes its state. In the quantum world, particles exist as probabilities rather than definite objects. But the moment they are measured, they collapse into a single, fixed state. This was demonstrated in the infamous double-slit experiment, where electrons, when unobserved, behave like waves, passing through both slits simultaneously and creating an interference pattern. But the moment we try to detect which slit an electron goes through, it suddenly behaves like a solid particle, as if it knows it's being watched. This raises a deeply disturbing question. Does reality exist independently of observation, or does it only become real when we look at it? Some physicists suggest that this effect hints at a more profound connection between consciousness and reality. Could human awareness play a role in shaping the universe? This idea is controversial, but has inspired wild theories, from the holographic universe hypothesis to the idea that the entire cosmos is a simulation. The observer effect also fuels the many worlds interpretation, which suggests that every quantum event creates parallel universes. In this view, every possible outcome exists, but we only experience the one that observation collapses us into. Whether reality truly depends on observation or not, one thing is certain: the quantum world does not behave the way we expect. And if that's the case, what other strange effects might be lurking beneath the surface of reality? Quantum tunneling, walking through walls. Imagine trying to walk through a solid wall. In the classical world, this is impossible. You'd just slam into it. But in the quantum world, particles don't always follow the rules of common sense. Thanks to a bizarre phenomenon called quantum tunneling, particles can sometimes pass through seemingly impenetrable barriers as if they were ghosts. Here's how it works. In quantum mechanics, particles like electrons don't move in straight paths like tiny billiard balls. Instead, they exist as probability waves, meaning they have a chance of being found in multiple places at once. When a particle encounters a barrier, you'd expect it to be stopped. But there's always a small probability that the particle's wave function will allow it to tunnel through the barrier and appear on the other side, without ever breaking it. This effect is not just theoretical, it happens all the time in the real world. In fact, quantum tunneling is essential for life itself. The nuclear fusion that powers the sun relies on quantum tunneling, allowing hydrogen atoms to fuse into helium despite energy barriers that should, in theory, make fusion impossible. Without quantum tunneling, the sun wouldn't shine and life on Earth wouldn't exist. Tunneling also plays a crucial role in modern technology, such as scanning tunneling microscopes, which allow us to see individual atoms, and quantum computing, where particles can jump past traditional computational barriers. But quantum tunneling raises unsettling questions. If particles can cheat the laws of physics, could macroscopic objects, like people, tunnel through walls? In theory, yes. But the probability of such an event is so astronomically low that you'd have to wait longer than the age of the universe for it to happen. Still, the fact that reality even allows such a possibility is proof that the quantum world is filled with strange ghost-like phenomena that defy everything we think we know. And if tunneling allows particles to pass through barriers, what about the fundamental limits of knowledge itself? That's where the uncertainty principle comes in. The uncertainty principle, why we can never know everything. In the quantum world, there is a fundamental limit to what we can know. This is described by Heisenberg's uncertainty principle, which states that we can never precisely measure both the position and momentum of a particle at the same time. The more accurately we try to measure one, the less we can know about the other. For example, if you try to pinpoint exactly where an electron is, its speed becomes completely uncertain. If you measure its speed precisely, its location becomes a blur. This isn't due to technological limitations, it's a fundamental property of the universe. The very act of measurement disturbs the system, preventing us from ever seeing the full picture. This principle shatters our classical view of reality. In the everyday world, we assume that objects have definite positions and speeds, whether we observe them or not. But in the quantum world, particles exist in a cloud of probabilities. They don't have a single well-defined state until we measure them. The implications of the uncertainty principle are profound. It means that reality at its most fundamental level is inherently unpredictable. Even if we knew every single law of physics, we still wouldn't be able to predict the exact outcome of a quantum event. Instead, we can only calculate probabilities, meaning that chance is deeply woven into the fabric of the universe. This also explains why electrons don't simply spiral into the nucleus of an atom. Because of uncertainty, they can never have both zero position and zero momentum, preventing atoms from collapsing. Without this principle, matter as we know it wouldn't exist. But uncertainty leads to even stranger possibilities. If particles don't have definite properties until measured, could time itself work in reverse? This brings us to one of the most disturbing ideas in quantum physics, retrocausality, the possibility that the future can influence the past. Retrocausality. Can the future affect the past? In our everyday experience, time flows in one direction, from past to future. Cause comes before effect. Drop a glass and it shatters. You never see broken shards reassemble themselves. But in the quantum world, things aren't so simple. Some theories suggest that the future might influence the past, an idea known as retrocausality. This bizarre concept emerges from experiments involving entangled particles. In some versions of these experiments, choices made in the present seem to determine how a particle behaved in the past. In other words, actions taken now could potentially affect things that have already happened. One famous example is the delayed choice experiment, a variation of the double slit experiment. If a particle is given a choice between behaving like a wave or a particle, and we delay the measurement until after it has already passed through the slits, the outcome still seems to be determined by the final measurement. It's as if the particle knew what we would do in the future and adjusted its past behavior accordingly. This raises disturbing questions. If the future can influence the past, does that mean free will is an illusion? Could choices we make today reshape history? Some physicists argue that retrocausality is simply a mathematical quirk, while others believe it hints at a deeper, hidden structure of time that we have yet to fully understand. If true, retrocausality could have profound implications for our understanding of time travel, causality, and even human consciousness. Could quantum mechanics be the key to rewriting the past? Or is it just revealing that time itself is more flexible than we ever imagined? Quantum vacuum fluctuations when nothing is alive with energy. In classical physics, empty space is just that, empty. But in the quantum world, even the vacuum of space is teeming with activity. Thanks to quantum mechanics, what we think of as nothing is actually a boiling sea of virtual particles popping in and out of existence, constantly appearing and disappearing in fleeting bursts of energy. This phenomenon, known as quantum vacuum fluctuations, suggests that space is never truly empty. Instead, it's filled with particles that borrow energy from the void, exist for an instant, and then vanish before they can be detected. These virtual particles might be tiny, but their effects are real. They contribute to the Casimir effect, where two metal plates placed extremely close together in a vacuum experience a mysterious force pushing them together, not because of any external pressure, but because of the energy fluctuations in the vacuum itself. Even more mind-blowing is the fact that quantum fluctuations may have played a crucial role in shaping the entire universe. In the earliest moments of the Big Bang, tiny fluctuations in the quantum vacuum were stretched by cosmic inflation, eventually seeding the formation of galaxies, stars and planets. Without them, the universe might have remained an empty, uniform void, devoid of the complex structures we see today. Quantum vacuum energy also ties into one of the greatest mysteries in physics: dark energy, the invisible force causing the universe to expand at an accelerating rate. Some theories suggest that dark energy might be a manifestation of the energy present in the quantum vacuum, meaning that empty space itself could be responsible for the ultimate fate of the cosmos. But if quantum fluctuations can generate energy out of nothing, could they also create entire universes? Some physicists speculate that our own universe might have emerged from a quantum fluctuation, suggesting that reality itself is built on the shifting, unpredictable nature of the quantum vacuum. And if empty space is never truly empty, what about the fundamental fabric of reality itself? This leads us to the final and perhaps most unsettling quantum mystery. Is reality just an illusion? Is reality an illusion, the simulation hypothesis, and the nature of existence? As we've explored the bizarre world of quantum physics, one unsettling idea keeps emerging. What if reality isn't what we think it is? The quantum world behaves in ways that seem to defy logic. Particles exist in multiple places at once. Entangled objects communicate instantly across vast distances, and reality itself seems to depend on observation. Some scientists and philosophers have taken this a step further, suggesting that our universe may not be real in the way we assume. One of the most radical theories is the simulation hypothesis, which proposes that our universe could be a highly advanced simulation. This idea, popularized by thinkers like Nick Bostrom, suggests that if advanced civilizations exist, they might have the computing power to create entire simulated realities indistinguishable from real ones. If so, how do we know we aren't living in one? Some aspects of quantum mechanics seem eerily compatible with this idea. The observer effect, for example, resembles the way a video game only renders what is being looked at, rather than simulating an entire world in full detail. Similarly, quantum entanglement and superposition hint at a level of interconnectedness that suggests a deeper underlying code governing reality, perhaps one designed by an unknown intelligence. Another perspective comes from the holographic principle, which suggests that the entire universe might be a projection from a deeper, lower-dimensional reality, similar to how a three-dimensional image can be stored on a two-dimensional surface. If true, this would mean that everything we experience as real is merely a projection of something more fundamental. Whether or not we live in a simulation, one thing is clear. The laws of quantum mechanics challenge our very understanding of existence. Reality is not as solid or predictable as it appears. Instead, it is a shifting, interconnected web of probabilities, consciousness, and mathematical patterns that we are only beginning to comprehend. As we continue to push the boundaries of science and technology, from quantum computing to deep space exploration, we may one day unlock the answers to these cosmic mysteries. Until then, The quantum world remains a realm where the impossible becomes possible, and the very nature of reality is up for debate. That wraps up the mind-bending journey through the spookiest laws of quantum physics. A reality where particles can be in multiple places at once. The future might influence the past, and the very fabric of existence seems to be woven from probabilities rather than certainties. From quantum entanglement to the simulation hypothesis, each of these ideas challenges everything we thought we knew about the universe. But despite their strangeness, they are not just abstract theories. They form the foundation of modern physics, shaping everything from quantum computers to our understanding of the cosmos itself. As we continue to explore these mysteries, one thing is certain. The deeper we dive into the quantum world, the more reality begins to resemble science fiction. Could we one day harness these effects for technology beyond our imagination? Could the answers to these mysteries reveal new laws of physics, new dimensions, or even new universes? For now, the quantum world remains an enigma, one that reminds us that the universe is far stranger, more mysterious, and more fascinating than we ever imagined.